So when last we left, it's page 24, we were talking about things that are stresses and things that are not stresses. And one of the things that is not a stress is changing the surface area because it speeds up the forward and reverse reactions by the same amount. So if we increase it, say, we speed them up by the same amount. If we decrease surface area, it decreases by the same amount. And we were just getting around to talking about saturated solutions when class ended. So a saturated solution contains the blank amount of blank possible. And we had been talking about the two components of solutions. What were the two components of solutions? Solute and solvent. And if something is saturated, yeah, it has the maximum amount of solute. I guess I should say dissolved. I should have put dissolved first, but I've got space for it here, so I'm going to put it here. The maximum amount of dissolved solute possible. So let's say we had a container like this, big wide container, okay, water. And say we have a big piece of silver chloride solid. Once the solution is full, in other words, once it has the maximum of silver ions and chloride ions, does it stop dissolving? Do no particles ever get bashed? Like a little water molecule is going to come over here and it's going to bash into the side of the AgCl and it's going to knock some of those ions free. So it's not like it stops dissolving, but the solution is full. So what has to happen if we have a saturated solution if some more dissolves? Another particle has to recrystallize. Often it's more, yeah, they will usually go on to the solid because they just sort of, it's like magnets clicking into place, you know, because it's like positive, negative. They won't tend to just, you know, partner up and float around on their own. Even if they do that, they'll be like, oh, look, here's a nice place for me to land. Yeah. So if you have a large surface, you have a large surface from which you can have the dissolving process happen. So the large surface is going to give you lots of places from which dissolving can happen, but it also gives you a large surface upon which dissolved particles can recrystallize. As opposed to if you had a smaller surface, right? You'd be like, oh, that's the only place that can happen, right? So if you increase the surface area, you're increasing the forward rate and you are increasing the reverse rate by the same amount. Yes? I don't know. Maybe, especially if you've got the water evaporating over time. Often, I'm just trying to think of a situation where that would happen. I don't know. Probably not, but you can, and well, You can end up with like bigger crystals forming, especially if the water is evaporating over time. Yeah. Yeah. They'll often use, in order to grow a really nice single crystal of a particular type, what they'll often do is they will super saturate a solution, which means they will heat it as they dissolve it, and then they will cool it very slowly, which then allows more ions to stay in than would normally dissolve at that temperature, because they made their way in there and then they're just kind of hanging out there. And then if you have a seed crystal in there, so you'll put like a little crystal in there that's a nice perfect crystal, and the crystal will start to grow on it. So yeah. All right. So right now, what you guys are going to do is on the next page, you are going to list 3 things which are stresses and list 3 things which are not stresses. See what you can remember. Yes.
This is the catalyst for the forward reaction also serves as a catalyst for the battery.
Yes.
How does volume impact one? Does that have everything?
Only if you have gases on both sides of the reaction. So if you have volume, like let's say you had A, which is gas, plus B, which is a solid, gives C, which is a solid, it's only going to affect the rate of collisions with A. Yeah? And then it actually, if you have a system where you have different numbers of gas molecules on either side, it will cause a shift. If you actually have the same number of gas molecules on each side, it will not cause a shift. Yeah. Yeah. No problem. You're good. You're good. Yeah. All right. So what are 3 things which are stresses? We could change we could change the temperature. What else could we change? We could change don't everybody answer at once. You all know this. You could change the concentration. What else could we change? Pressure, volume. Yeah. What are 3 things that are not stresses? Yes. Catalyst. What else? Okay, everyone. What else? Pardon me? Surface area. And there's one more. Adding an inert gas, yes. All right, for the things that are stresses, these 3 make the forward and reverse rates temporarily unequal, and that's why we get a shift. So they can do this either by changing only one of the 2 rates, either the forward or the reverse. The factors that do that are pressure, volume, and concentration. Or we can get changing both rates, but by different amounts. What factors do that? Temperature. And if you happen to have gases on both sides of the equation, pressure, volume, different amounts. These other ones are catalyst, surface area, and inert gas. Leave the forward and the reverse rates the same. And they do this either by increasing, I guess I should say decreasing / increasing both rates equally. Which things change both rates equally? Catalyst. What else? Surface area. Or they can do it by not changing either rate at all. And the factors that do that are the inert gas. Now, I have to say the situation that you were talking about, Ansel, was when we had, if we have the same number of gas molecules on each side, it will actually change both rates the same. So I'm going to put that in brackets over here. Pressure, volume, if there's the same number of gas molecules on each side. So pressure volume doesn't fit entirely into any one of these categories. It's totally dependent on whether you have gases at all, or whether you have same number of gases on both sides, or whether you have different numbers of gases on both sides. So you got to think about gases a little bit more. All right, the shift is in response to a stress, and it happens until a new equilibrium is established. So the shift, which is what we do, and the response, oh, no, I'm a dummy. The stress is what we do. The shift is what the system does. So we're going to use our reaction that we had yesterday, the one that was N2O4. Gives 2 NO2. All right, and we have our forward, and that's our rate. And we have our reverse rate. And let's assume we add right here, we're going to add N2O4. What happens to the rate? Forward rate goes up. So that right there, that vertical line is our stress. And then our shift, what's going to happen to our reverse rate in that same moment? It's going to stay the same because we haven't done anything to the amount of NO2, so there won't be any more or fewer collisions. But as time goes on, what's going to happen to the forward rate? It's going to decrease. Is it going to decrease as a straight line? what's it going to decrease like? Like that kind of thing, yeah? Okay, so it's going to go down in a curve. And what's going to happen to our reverse rate? It's going to increase. And it goes up in a curve until they meet in the middle, somewhere in the middle. And this section here, this section is the shifting section. Is good? So we have our stress, we have our shift, and what happens when they meet? What's happening right when they meet? We have a new equilibrium. And over back here, we had our old equilibrium. Okay. So that's what rate diagrams are going to look like. You're always going to get that meeting in the middle because they're always going to come back to some sort of equilibrium unless you have an open system, okay? Or if you keep things changing. The curves, the curved part, which is in the shift section, should always be initially steep, and it should be more shallow as time goes on. So the rate of change of rate, the rate of change of the rate, that's crazy, is fast at first, and then it changes less and less as time goes on. Okay. All right, so sample problem number 1. Let's label on here the old equilibrium, the stress, the shift, and the new equilibrium. Take a moment and do that. You can label them however you want. If you've got some highlighters, you could have, say highlighted the shift and be like, the shift is this little blue section here, right? Or whatever. You're really not going to have to do this labeling process, but you need to be able to recognize each part of the graph for what it is, okay? At the moment of the stress, what happens to the forward rate? And I'm afraid it doesn't show up well on your book, so it's a good thing that we've got this up on the overhead. The forward rate is the red one. At the moment of the stress, what happens to the forward rate? The forward rate increases. Ooh, and it's the reverse. And the reverse rate, what happens to the reverse rate? It stays the same in that moment of the shift. During the shift, At the beginning of the shift, are the slopes steep or shallow? Steep. That means that at the beginning of the shift, the rates are changing. Are they changing slowly or quickly? They are changing quickly at the beginning of the shift. Are the slopes at the end of the shift steep or shallow? They're shallow. This is all difficult to say with my Invisalign. I'm like, there's too many S's and the shift steep. Okay, anyway, they are shallow. This means that at the end of the shift, the rates are changing slowly. Okay, sample problem number 2. Label the old equilibrium, the stress, the shift, and the new equilibrium. So once again, now this time you don't have a rate diagram, you have a concentration diagram. What was the stress? Yeah, it was an increase in S and NO, yeah. Increase in the concentration of NO. Excellent. All right. Are the slopes at the beginning of the shift steep or shallow? Steep or shallow? Steep. You will be expected to show those slopes being steep at the beginning. Don't make them shallow. They'll end up looking like S's, and I'll show you a little bit more later about that, but no S curves, okay? This means at the beginning of the shift, the concentrations are changing quickly or fast. Are the slopes at the end of the shift steep or shallow? Shallow. And that means that the concentrations at the end of the shift are changing slowly until eventually they don't change at all. Okay, and that's when they flatten out. Concentration, I don't know why I have this word here. Let's get rid of that. Let's fix that. Concentration is an example of what type of property? Macroscopic, yeah. Of a macroscopic property. Concentration is constant at equilibrium. Hang on one second. I'm thinking maybe I have this somewhere else. Hang on one second. No, I don't. Okay, while we're here, I would like you to tell me examples. I think there's another place for this, so we may end up doing this twice, although we won't write it the second time. Examples of other Macroscopic properties. Yeah, I'm pretty sure it's somewhere else. Tell your neighbor, what can you think of that are also macroscopic properties? And if you're having any trouble, here's a hint. A lot of them are properties that can be monitored if you have a reaction going on to measure its rate. But they become constant once a system reaches equilibrium. Okay, what's one? What do we got? Temperature. We already had concentration, so I'm just going to list that one. Color. Surface area. And surface area doesn't necessarily have to remain constant. Because what could happen is if I had a system that was at equilibrium and I then shook the container and I broke the solid apart, if there was a solid, it would still be at equilibrium, assuming there was maybe a gas in there or something, but it wouldn't change the amount that was in gaseous form, right? Mass, yes.
So do macroscopic properties, are they only like things they use?
They are things, they are macroscopic properties are just observable properties. What would not be changing when you're at equilibrium?
Observable during a reaction.
I mean, if you're saying during a reaction, that implies that the reaction is happening and then it's going to be over and we had a one-way process. Yeah? So at equilibrium, you would be observing that these things are not changing.
So macroscopic properties are constant?
Yes. Macroscopic properties are constant at equilibrium. Yes.
Would you not use the term macroscopic properties in street code and equilibrium?
No, not really. It's not used in other contexts, really. Yeah. Sorry? Absorbance. Yeah. That goes with color too. Absorbance, pressure, pH, volume. Okay? All of those are macroscopic properties and all of them are constant at equilibrium. Yes? Microscopic properties are better expressed as particle level properties, which means that the particles are swapping atoms, which is why they're not constant. We don't actually say microscopic properties. We say there's no changes at the macroscopic level, but there are changes at the particle level. Okay? But you could also express that as there are no macroscopic changes, but there are microscopic changes, which means there are changes at the particle level.
Are there examples like temperature,
No, you just be like, this particle used to be made of these two atoms. This is number 1, this is number 2, right? And now, okay, let's do 1 and 2, 4. And then we have over here 5 and, oh, sorry, 6, 7, and okay. Now, later, you would have 1 and 7. Yeah? You know what I mean? Like those are happening. Yeah? Okay, I drew way too much for that, but yeah. So those are particle level changes, but it's not something you can observe, okay? All right, so this is just a picture of those two diagrams. When a system is at equilibrium, forward and reverse rates are equal. The concentrations are, they are constant, but they are not equal. So products don't equal reactants. A stress in a diagram is signified by a vertical line, except for temperature in a concentration diagram. But most of the time it's a vertical line. And temperature in a rate diagram is still a spike. We'll get into all of these examples later. And a shift is shown as a smooth curve. Now, I don't know exactly how to put this, so I've done my best. Basically, you need that rate of change to be the fastest at the beginning. Okay, so when we look at this, these are good. You get these little sharp points here, and that's because you have the fastest rate of change at the beginning of the shift. Okay, it is the steepest at the beginning of the shift. So you end up with these sharp little points. Now, the reason I don't like that language is if you do it wrong, you can still have some sharp points, but some of them will not be sharp. The basic thing that is wrong with these, what is the basic thing that's wrong with the ones on the right? Yes? Oh, I thought you had your hand up. Never mind. Never mind. Yes? Pardon me? They're curving in 2 directions. So what this is saying is it is saying the rate is changing slowly. Then the rate changes quickly. Then it changes slowly again. Or in this case, not rate. This would be concentration. Concentration changes slowly, then the concentration changes quickly, then it changes slowly again. Does that make sense? No. Okay, this bit where it changes slowly at the start is incorrect. That's just wrong. It always changes quickly at the start. So you need to have the steepest part needs to be at the beginning of the shift. And these all have shallow. So, like I said, I'm never quite sure how to put this so it makes the most sense, but basically no S curves. Okay, you don't want these things to look like S's when you draw them. If you draw an S while you are drawing a rate diagram or a concentration diagram, you will lose marks. We do a lot of fudging in these diagrams, like they're not accurate in terms of where the concentrations end up or anything like that, but there are certain things that you need to be precise about, and that's the shapes of the curves, okay? Steep at the beginning of the shift. That is correct. Yay! Okay. So we good? Excellent. All right. Same thing applies to rate diagrams, just like concentration diagrams. You should have sharp, no S curves. The other thing you have to watch out for is, and it depends on how good you are at freehand drawing, if you can draw a straight line and be like, oh, look at that, I drew a straight line. Yay, that's great. But if you draw a straight line and it looks like these ones over here, that is not a straight line. That is curving up. This one's curving up. This one's curving down, right? They're not straight lines. So do yourself a favor on a test or whatever, use a ruler. Okay, for yourself when you're drawing, I don't care, you know, whatever, doesn't matter. But when you're doing it on a quiz or a test, use a ruler. A curved line would imply that the concentrations were changing while the system was at equilibrium. Ah, that is wrong, because at equilibrium, the macroscopic properties are constant, and this includes concentrations. And this is where I was thinking, what are some other macroscopic properties? And if you want to fill that in some other time for yourself, you can, but we're not going to do it twice. Okay? Alrighty. Ooh, 2.2b. So we're going to focus in on the stress of changing concentration, because it's kind of the easiest one to think about. Not that the other ones are that hard, but this one's really straightforward. Stresses always make the rates unequal. The shifts make the rates equal once again. So here we have the reaction H2 plus I2 gives 2HI. And we are going to start by drawing what this system looks like if we are at equilibrium. And we are going to be drawing a rate diagram. What can we say about the forward and reverse rates if we are at equilibrium? Yep. Forward rate is the same as the reverse rate. So if we're going to draw these, and if you happen to have two colors of pen, you can use two colors, or you can just do like forward and dashed line for reverse. That also works very well. So we're going to start at an initial equilibrium where the two rates are the same. This is our initial equilibrium. And now, on our next graph, we're going to introduce the stress. And what is our stress going to be? It is going to be an increase in the concentration of H2. And I'm just going to rewrite our equation here so it's right in front of us, H2 plus I2 in equilibrium with 2HI. Rate goes on the Y, time goes on the X. We have the initial equilibrium where they are the same. And then during the stress, What happens to the forward rate? Increases. Does it increase like this? Does it increase like this? Does it increase like this? What do we like? Third one, okay, because it's a stress, instantaneous. Whoops, that wasn't supposed to attach. Why does the forward rate increase? Yep, higher concentration of reactants. And therefore there will be more frequent collisions. Whenever you're talking about rate and you're explaining rate, you should probably always bring it back to collisions. Okay? What happens to our reverse rate in that same moment? Nothing. There's no change. Why not? No change in concentration of the products. Therefore, the same number of collisions, same frequency of collisions. So at this point in time, now there's different usages of the word favored. We can say products are favored, which means when we are at equilibrium, we are sitting more towards the products. We got more products than reactants. We can say the reactants are favored, which means at equilibrium, we are shifting, we have more reactants than products. But we can also say during the shift, which reaction is favored. And when we use it that way, we're meaning which reaction is happening more, which one is happening faster. So when we're using it in terms of the reaction that is favored, that means which reaction is happening more or going faster. Which reaction is favored, forward or reverse? Forward. Excellent, let's keep going. So as a result of the forward rate being faster than the reverse rate, the system is now shifting. And I'm just going to write our reaction again here so we can remember what it was. H2 plus I2 in equilibrium with 2HI. As it shifts, ooh, I did that wrong. I really wanted to do it like this, because my forward rate is faster than my reverse rate. So I wanted to draw it like that so it's quite obvious what's happening. What will happen to the concentration of H2? It will decrease because we're using it up faster than we are producing it. How about I2? Same thing. It's going to decrease. We're using it up faster than we are producing it. And HI? HI will increase. As a result of these concentration changes, H2 is decreasing, I2 is decreasing. What's going to happen to the forward rate? It will decrease. It decreases as the H2 and I2 decrease because that results in fewer collisions. I should say results in less frequent collisions. So now we're carrying on with our graph. We have the forward. We have the dashed line for the reverse. We have our initial equilibrium. We had our stress, which was to add H2, which it caused our forward rate to increase and our reverse rate to stay the same. That was our stress, but now we're moving on to the shift. During the shift, what is happening to the reverse rate? Reverse rate increases. Tell your partner why. Why, while we're shifting, does the reverse rate increase? I didn't want to interrupt you. That sounded amazing. I was like, oh no, you're just doing such a good job there. Anyone want to tell us? The reverse rate increases because? Yeah. As the concentration of HI increases, the frequency of collisions increases, because always bring it back to collisions. All right, and so now what shape should these curves take? Yep, they should go steep and then shallow and then flat. Steep, shallow, flat, and they should meet somewhere in the middle. Steep, shallow, flat, steep, shallow, flat. Meet in the middle. So that is a rate diagram for what happens if we change the concentration of H2. Next thing we're going to do is draw a concentration diagram. Now, concentration diagrams, it doesn't matter which chemical you put where. We're just assigning them arbitrarily. We're just looking at what changes about them. It's really the changes that matter. So to make my life really easy for now, I'm just going to, it goes H2, I2, HI, so I'm just going to put them H2, I2, and HI. And that just means that your notes are going to match this morning's group's notes. And there's our concentration. And then, of course, we have time. And at time t, we increase the concentration of H2. What's that going to look like on the graph? Vertical line, where? H2. Any of the others? No, they just stay there and do nothing. Okay, so that is our stress. Now, as we have that stress, which way will the equilibrium shift? It's going to shift to the right. Now, if you want this in terms, an explanation of the shift in terms of Le Chatelier's principle, I forgot an N. Principle. Best explanation is always in terms of rates. You would say, I have more reactant particles, therefore my rate is faster in the forward direction, but now I'm making more product particles, so my reverse rate is going to increase. I'm using up reactants, so my forward rate is going to decrease, and therefore I am shifting to the right. It's long and involved, and I don't even think I said it right then. I would need to, think it through a little bit more clearly than that. But the Le Chatelier's principal way of explaining it is you would say, we increased the concentration of H2, therefore the system shifts. Remember, whatever we do, nature tries to undo. However, are you ever going to write that anywhere on an official paper of any kind? No, because that is a bad explanation. Because does nature really sit there and think, it's a change? I don't like change. Don't make me change. I'm going to get it back the way it was. Is nature sitting there having feelings all over the place? No. Okay. We increase the concentration of H2, therefore the system will shift and you don't just say to minimize the stress, because that's not specific enough in this case. That's what Le Chatelier's principle says in general. When a stress is applied to a system, the system shifts to minimize that stress. But what we would say is it will shift. What would minimizing this stress be? To decrease the H2, right? To bring concentration back down to close to its original level. So what that means is that if this is my original concentration of the H2 is going to now decrease in the whole steep, shallow, flat manner. Steep, shallow, flat. And it gets close to its original level, but not quite. Yeah? So whenever you have a concentration being the stress, the thing that was, if you increase it, it will get close, but a little bit higher. Because you've simply got more atoms in the system, you're going to end up with more of stuff. Okay? Now, what's going to happen to the concentration of I2 as we shift to the right? I2 is going to decrease. By how much? As much as H2, okay? So these should be the same size, and the curves should end at approximately the same time. Do your best to make that happen. I don't always succeed. I am not drawing a straight line here to save my life. Okay? And if you're like, you know what, mine actually don't look like they are the same, what you can do is you can go, this distance here is X. This distance here is X. So even if you draw them and they don't look anything like the same size, you have told me they are supposed to be the same size, even though I can't draw. Okay? Because sometimes I can't draw. Sometimes you can't draw. HI. What will happen to the concentration of HI? It's going to increase by how much? Twice as much, because we have a coefficient of 2. All right, we got a 1 and 1 and a 2. So it's going to go up by twice as much. So we're going to be like, okay, maybe I'll do it in blue because everything's coloring. Steep, shallow, flat. I would probably want to go over that flat part with a ruler, but I'm not going to bother right now. Okay, and then I would say, okay, going up there, that is going to be 2x. Is good? Okay. And the system has shifted right, but we already said that, so I don't know why I need to mention that. Okay. Whoa, what happened? That was crazy. Come back. No, not like that. Okay, hang on. I keep clicking the wrong thing. Hold on, hold on, hold on. It's this one. I want that one. There we go. All right. Okay. So when we increase the H2, the stress shifted the system to the right. Are there any other concentration changes that we could make to shift the equilibrium to the right? And actually, before we do this, I'm going to tell you about something that I told my other class about. I usually talk about it a little bit later, but I liked this. If we have our H2 plus I2 in equilibrium with 2HI, what I imagine for myself when I'm trying to predict which way it's going to shift, of course I can think it through, but sometimes I like a really quick visual. So what I'll do for myself is I will say H2 is increasing. So I'm going to draw an arrow there. And then I'm going to pretend that I have a sort of pulley system where I've got a little pulley here and a little pulley here, and I've got a chain that goes all the way around like that. Yeah? Now, if this side is going up, which way does the top part of the chain move? To the right. So if I increase something on the left, it's going to move to the right. If I were to decrease concentration of H2, that would cause the chain to move to the left. If I pull it down, so if I pull this way, it's going to go that way. If I pull it that way, it's going to go that way. So you can just imagine what's happening at that top part as I either go down on one side or push up on that side, go down on the other side, or push up on that side. What's happening to that top part of the chain? That's how it shifts. John is giving me the look that I expect. No, I every time I teach this, the first time I teach it, I get whole bunches of people who are like, what are you talking about, Ms. Spence? This is the stupidest way of doing it ever. And then, but I encourage you to stick with it, even if you hate it right this second, because you may learn to love it. Okay? You may also never learn to love it, and that is okay. You never have to use it, but I'll keep harping on it because it can be a really quick visual way of determining the direction of the shift very quickly. Okay, are there any other concentration shifts other than increasing H2 which could shift our equilibrium to the right. We could increase the concentration of I2. So number one, we could increase the concentration of I2. And this time, I'm going to put my HI up top, just to prove to you that it doesn't matter where I put these things initially. I'm going to put my H2 here. And I'm going to put my I2 here. And I'm going to try and draw a straight line there. Hello. Yeah, we have okay, this one's for you. Anytime you want. Okay, and Dylan, this one is for you. So this is a concentration diagram. So we label it concentration. On the x-axis, we put time, and I2 increases. Could I make I2 increase past the level of H2? Yes, it just drawing becomes awkward at that point. So we try and do things that make our drawings less awkward. So usually I would stop before I get to the level of another thing. Otherwise, it just gets messy. Okay? And if we increase, that is going to shift to the right, which means we are going to have a decrease in I2. Where will the decrease for I2 stop? Is it going to stop at line A, line B, or line C? A, okay? It should be above the original amount. Okay, that's a terrible straight line, but we're going to pretend it's okay. There we go. All right, H2, what will H2 do? It will decrease by the same amount. Okay. And then HI is going to increase by twice as much. Now, if you were to look at that, and I did this on purpose, but I could have done it accidentally, do those look like they are in the correct proportions? Not really. So what I would do is I would be like, I don't really want to redraw the whole thing. So I'm going to say that that distance is X. This distance is X. And this distance, I'm going to label it as 2X. And that makes up for my horrible drawing. But I would normally try and draw better than that. Okay? Any other changes we could make to get the system to shift to the right? We could decrease HI, absolutely. All right, and this time we're going to have HI on the top. We're going to have, let's put I2 next. Why not? Doesn't matter. Let's put H2 next. All right, so we decrease HI. Oh, okay, here we go. There we are. And it's going to go back up. Where does it go to? How far does it go back up? Does it go here or here or here? First, second, or third? Third one, okay? Lower. It will try to get to its original concentration, but it won't quite make it. And now that value, because the HI has a coefficient of 2, that's going to be 2x. And that means that H2 and I2 are going to decrease by x. And I'm going to do a better job this time, I promise, of doing that sort of x. X. And now we are going to start. Maybe I just give you homework. You guys are going to do pages 20 to 23 in the pink book and 46 in the blue book. If 20 to 23 seems like too much, just make your way through part of it, okay? But don't neglect the blue book, because this weekend you get your practice test. Woo! An actual test, no. Not unless you want to. Didn't think so. 6. Reaction rates is the shortest, but it also has the most extra AP stuff, because I throw in spectrophotometry in there as well. And it's got all the reaction kinetic stuff. The other units don't have nearly as much extra AP stuff. Some of them don't have any. So.
How much stuff do you have on ladder?
Lots. If you ever want to know the percentages that'll be on the exam, what do they call it? Breakdown of the AP exam: atomic structure and properties, 7 to 9% of the exam. Compound structure and properties, 7 to 9% of the exam. That's like bonding, and those resulting properties. Properties of substances and mixtures, how they form solids, liquids, and gases, and how the forces that influence those states of matter, 18 to 22%. Chemical reactions, 7 to 9%. And what happened to the rest of it? I don't know. Exam description, that's what it's called. And you can actually download this whole thing if you want to. AP Chemistry course at a glance. Properties of mixtures, 18 to 22. Kinetics, 7 to 9. Thermochem, 7 to 9. Equilibrium, 7 to 9. Acids and bases, 11 to 15. Thermodynamics and electrochemistry, 7 to 9. So most things are 7 to 9%, except with a couple of exceptions. Acids and bases are big. Properties of substances and mixtures, IMFs, interparticle forces, properties of solids, all the gas stuff, solutions and mixtures, separating solutions and mixtures, solubility, spectroscopy, Beer-Lambert law, properties of photons. That's a big section. I don't necessarily agree with how they've organized it, as you can see by the fact that I did not follow their organization, but whatever. Have you guys all signed up for AP Classroom? If you have not, make sure you do. You can go on there anytime you want. And I think I've assigned all the progress checks for everything we had done up until September. I will put reaction kinetics up there as well now because we've also already done that. See you guys later. Hi. Yeah. Sure. Yeah. Yeah. Yeah, that'd be fine. Yeah. Okay, good.